Hey all, I know this is a fairly large, it seems like a lot of information, and it is. I think gravity makes it feel like a little bit more than it really is. But remember, gravity and electricity are very similar. So let's jump right into it. First off, multiple choice questions are all going to come from electricity. Looks like no gravity. Type multiple choice questions. They'll come from just the notes there. So, first question, why don't you feel electrical forces that act on you all the time? Well, electrical forces, most objects have equal positive and negative. So we say that they are balanced out. So you have equal positive and negative charges, no charge. So that object is not charged. Even though it does have positive and negatives, you can't feel it because there's no charge and two neutrals don't attract. Blank is a fundamental electrical property to which the mutual attractions or repulsions fundamental. So gravity, it was mass, charge that causes electricity. My convention was the charge of the following. Remember, I told you it's a really small number, 1.6 or 1.9 times 10 to the negative 19th, 1.7, I can't remember the exact number, coulombs, but we just say that it is negative, protons are positive, and neutrons are neutral, or zero. Is the following sentence true or false? Mass of a proton 2,000 times, yes. True. Protons and neutrons are where the mass of the thing is, so moving electrons from particle to particle or object to object does not change mass, and that's what happens. Electrons move. Like charges repel, and opposite charges attract. Just a reminder, the question's going to be about that. All right, conservation of charge. The idea that if you lose negatives, something else must have gained those negatives. So the blank of many atoms are bound very loosely. So electrons are bound very loosely to the atom and can be easily dislodged. So electrons are the ones that can move. So we eliminate it down to A and B, and it's only the outermost that really get knocked off. The innermost stay there. So A is the answer. If a rubber rod is rubbed by a piece of fur, so we've got rubber, silicon rubber, balloon on fur, hair, things like that, the rubber becomes negative and the fur becomes positive. And that's that triboelectric series. Now, I'm not going to ask you one that has you memorize this. If you need this chart, if you needed to reference rubber and fur, well, then I would give you this chart here to look at. So remember, the ones up top said positive, the ones on here said negative, means these are going to become negative, these up here are going to become positive. So again, I would give you this if you need it. All right, Coulomb's law, or the electric force. The SI unit of charge is the coulomb, named after Augustin de Coulomb. How many electrons are contained in 1 coulomb of charge? We didn't really talk much about this, but the key is it's a lot. And the exact number is, I believe, 1.6 times 10 to the 19th electrons. Big number. Is the following sentence true or false? The electrical force between two protons is very small compared to the gravitational force. No. Gravitational force is very weak. Between two protons, very, very small. Electric force is the big one. So that would be false. Gravity is weak. Electric, we say, is strong. Or stronger, anyway. All right, conductors and insulators. We talked about this during the discussion. Material through which electrons can flow. Electrons, or electric charge, so charge can move, electrons can move, is the conductor. All right, and then the insulator is the one that they don't flow through. Oh, there it is right there. Material that is a poor conductor of electricity, or better stated, charge, is called an insulator. All right? Think about charges are what's moving. Electricity is the moving charge. So electric field. So now we're getting the idea of a sphere of influence around an object. What is an electric field? All right, that's that sphere of influence Sphere of influence around a charge. So the sphere of influence around a charge that tells how the other charges will feel a thing. The direction of electric fields point by convention at any point is the direction of electrical force on a small negative test charge placed at that point. No, not negative. False. The electric field points in the direction that a positive charge would feel a force. And test charge is just the word we use for that. But it's positive is what you want, not negative. Center of the electric field around a small positive charge. So here we go. How can you describe the field? So it'd be straight lines pointing away. Right? It's the direction that a positive would feel. So if I put a positive right there, it's going to be repelled away. And so we'll have our lines that all point away. So we'll draw it, but then you describe it there. So a little bit more exact, not just fields, but actually drawing the lines. Field lines can also be described by using fields. Field line represents the electric field. The field is weaker where the lines are far apart. Remember, the closer together the lines, the stronger the field. So match the illustration to the correct description. So here we go. We got a positive charge, positive, negative, and two parallel plates. Field lines emanate from a positive charge and terminate on the negative charge. So the one where they leave the positive, go to the negative, that's going to be B. Field lines are evenly spaced between two oppositely charged plates. This is that uniform field, and you see they're nice and even between the plates. That's C. And number 9, field lines extend to infinity. So this is the ones where they just keep going forever and ever, and they're going to get further and further apart, which means they get weaker and weaker. Okay. All right, a little quick transition to potential energy before we jump to potential. Remember, we had to kind of talk about electric potential energy before we get to that doesn't make sense for us. Let's use potential. Is the following sentence true or false? A charged object has potential energy by virtue of its location within a field. Remember, we drew the electric field between two plates, and this charged particle would have energy because that energy is its charge times its field times its distance. If there was no electric field, there would be 0 there, and it would be 0 energy. So it has energy because there's a field. Same thing with gravity. You have gravitational potential energy because you're in a gravity field. If there's no gravity, there's no gravitational potential energy. So this would be true. All right, but again, we don't use just one charge. We use lots of charges when we talk about electricity and the flowing, so energy for a single charge doesn't make sense. We use the idea of potential. What is electric potential? Simply stated, it's energy of electricity, but it's per charge. So it's per coulomb of charge. It's not the energy, it's energy per charge. So that if it's flowing energy, right, you think about flowing, then we can talk about the potential here versus the potential down here. I don't know how much is flown past here, how much electricity is flown through here, but we know the energy coming in and the energy going out per charge. So that's why we use potential. The following sentence, true or false? Electric potential is not the same as potential energy. Absolutely. True. Potential is energy per charge. Energy is just the energy, a number. SI unit measurement for potential is the volt, abbreviated V. All right, an equation expresses the relationship between volts, joules, and coulombs. Actually, we're not going to worry about that. All right, and voltage is energy per charge. For this one, you don't need to know an equation. You should definitely know the difference between potential, energy, and charge, like that warm-up with the batteries, but you don't need to know an equation for it. All right, so storage of energy. This is that whole idea of storage between two plates. We did the capacitor, building it up. Charge capacitor is discharge when blank is provided between the plates. When a ground, or really we should say path is provided between the plates. So this is, you touched the wall, it was able to jump and discharge, but before that it couldn't discharge the capacitor. So a path is provided between the plates. The energy stored in the capacitor comes from the work done to charge it. We say work, remember work is the transfer of energy. Whatever energy you put in is the energy stored in it. All right, flow of charge. Charge flows when there is, well, you got a conductor. Here's my wire. Maybe I even put a light bulb in it. All right, so here I've got the two ends of a conductor. With my light bulb in here, charge flows. Charge is going to flow through this when I put what here? I need a voltage. All right, I need some sort of positive, negative voltage. It could be a wall outlet, it could be a battery, I don't know, but I need to put a voltage, then it will flow. So what would happen if a Van de Graaff generator charged to high potential was connected to a ground wire? Well, it would discharge and it would flow, so we'd have current. The electrons would leave the Van de Graaff and flow down to the ground, and we'd have what we call current, or the flow of charge. Right? And that's what you all felt. You all felt that nice charge thing, the current, that flow of charge going through you is what you felt when we did the activity. And explain how a sustained flow of charge is now to the flow of water in a higher reservoir to a lower one. And that's the idea of that waterfall up top down to kind of a waterfall down below. All right, where we said it was like energy, high energy per charge, or per thing. Energy high, and it will flow down to a much lower amount of energy down here. Right? And so we have a high potential down to a low potential. All right, so then we get to electric current, match the phrase with the correct term. And we're going to use it more than once. We've got 4 terms here. Amp, unit for current. 0, conduction of electrons, that's going to be sure that's the flowing charge, right? Conduction, and then electric current is also the same thing. So the flow of electric charge is current. So it's going to be D. Particles within a solid conductor that carry the charge through a circuit, those are the electrons. So the particles that carry the charge, they are the charge, they move through, so those are the electrons. C. SI unit used to measure current, so the unit for current is the ampere. 1 coulomb of charge per second, that's an amp. 1 amp is equal to 1 coulomb per second, charge per second. So that would be A. And the net charge in a current carrying wire, so what is the net charge within a wire is 0. So there's still protons and electrons inside a wire, so even though the electrons are flowing through it, there's still 0 charge. So the wire itself does not have charge. All right, resistance. Following sentence true or false. The amount of charge that flows through a circuit does not depend on the voltage provided by the voltage source. So it's the amount of charge. No, absolutely. If I increase voltage, the current, or the amount of charge, is proportional to the voltage. So if I increase the voltage, that will increase the current. So this sentence is false. One more time. The amount of charge, current, that flows through a circuit does not depend on voltage. No, absolutely. Current depends on voltage. So what is resistance? Well, resistance is a measure of something's resistance to current. Measure the resistance to the flow of charge. All right, electrical resistance is measured in what we call ohms. Electric resistance is measured in ohms. All right, Ohm's law. So this is the relationship between current, voltage, and resistance. I, V, R. And then Ohm's law, let's do it mathematically, V equals IR. Ohm's law, you would want to say, you don't need to write anything. We could just say that current is proportional to voltage and current is inversely, fishy symbol, proportional to resistance. So this is stating the law. This is how we said it mathematically. I know that looks a lot like math, doesn't it? You could write this out as words. Current, like you did with your 2 claims. You put your 2 claims. As voltage increases, current increases linearly. As resistance increases, current decreases inversely. So you could write all that out, and that would be the same thing. Or just write that. Is the following sentence true or false? A bird's perched on a high voltage wire. So you've got a bird. So here's this thing with some big, we'll say like 2,000 volts up here on this top wire. If I put a bird here, this is saying the bird perched on the wire is not shocked because there's no potential difference between one part of its body and the other part. All right, if you put it up here, this bird is going to jump up to 20,000 volts. But it's not going to discharge through it. It's just going to be at 20,000 volts like the wire. There's no path to go down to the 0 volts down here. That doesn't exist, and so this would be true. Electricity is not going to flow through this bird. It can sit fine at 2,000 volts, just like you can stand with your hand on the Van de Graaff and I can flip it on. You don't discharge, you don't get shocked or anything until something comes and touches you and discharges you down to 0 volts. Same thing with the bird. And that does it for the multiple choice. So now we get into kind of the calculation stuff. We've got about 3 pages left. So start out with a calculation for gravity. The mass of the moon orbits the mass of the Earth, so Earth-born at a radial distance, average distance of this. What is the gravitational force? Centripetal is the circular motion word for it. It's gravitational force that holds it in motion. Calculate is basically just calculate it. Well, I'll say universal gravitation. So gravity equals that, and then I'll plug in my numbers. So that will end up being 6.67 times 10 to the negative 11th times mass of the moon, 6.35 times 10 to the 22 times mass of the Earth, 5.97 times 10 to the 24th. All divided by the distance, 3.84 times 10 to the 8th, squared. Don't forget the squared. You're going to forget the squared. Don't forget the squared. All right, and that gets you most of the points. It's 4 out of 6 so far. We'll get the number, and the unit will be the other 2 points. So let's get that. You can't see me typing. 6.67 second EE, negative 11. No times 10, no caret, no nothing. Times 6.35 EE 22 times 5.97 EE 24. Can't see me typing again. And then I'm going to say divided by 3.84 EE 8. And then that's just going to be squared. Enter. And I get my answer. Yeah, it's a big number. 1.71 times 10 to the 20th. There's my 5th point. There's my 6th point. Newtons. Newtons of force. All right, the first experiment. So then we get into the idea of charging. The first experiments of electrostatics, Ben Franklin took a glass rod and rubbed it with a fine piece of silk. If you had that triboelectric, we could start thinking about that. We don't. This charged glass rod, with what we know, this charged the rod with positive charge. So now we know the rod became positive. What's the charge on the silk before being rubbed? Well, it was neutral. The silk was neutral prior to being rubbed. What's the charge on the glass rod before? It was also neutral. What is the charge on the silk after being rubbed? Like, oh, I don't know. It's going to be charged. I don't know if it's positive or negative. Look back up here. If the rod became positive, well, then the silk must have become negative. If the rod lost electrons to become positive, then the silk gained them to become negative, which has a larger net charge. Net charge means ignoring negative or positive. Key is they're the same. Whatever electrons the glass rod lost, the silk gained. So if this is positive 10, this will be negative 10. So it's conservation of charge. All right, Coulomb's law. Now we get to that double, triple thing. So 2 charged objects placed near each other to start. Distance between them becomes 4 times the distance. How much weaker or stronger does the force become? Remember, we can do that ratio thing. So let's do that. Kc, Q1, Q2 over D squared, ratio 2. Okay, now let's change something about it. Kc didn't change charge, and we said 4 times the distance. All right, simplify that. This squared comes in, I get 16D I also then cancel d squared, and I'm left with 1 to 1 over 16. And so it becomes 1/16 as much, which we'd say is weaker. So it's it says how much though, how much weaker. So it's 1/16 is weak. All right, two charged objects placed near each other to start. If the charge on one of them doubles while the charge on the other triples, how much weaker or stronger does it become? Same thing. Kc Q1 Q2 over d squared. Ratio 2, now let's change the stuff. Kc double 1, 2Q1, triple the other, Q2 over d squared. 2 times 3 is 6. So now I can cancel. And I'm left with a 1 to 6 ratio, and so it is stronger by 6 times. All right. Now, calculation with it. You also need to be able to calculate what's the force acting between 3 microcoulomb charge and 4 microcoulomb charge that are placed 0.05 meters apart. Kind of close. So let's do it. Equation, electric force, Kc Q1 Q2 over d squared. Plug in our values, 9 times 10 to the 9th times 3 times 10 to the negative 6. Remember, micro is times 10 to the negative 6, so it becomes 3 times 10 negative 6 times 4 micro times 10 to the negative 6, all divided by the distance 0.05 squared. And then I'll plug in to the calculator. So 9E9 times 3E negative 6 times 4E negative 6 divided by 0.05 squared. And I get 43.2 newtons. All right, last one though. I didn't ask it, but you need to know. Is it attractive or repulsive? Well, I don't know. Look, positive charge, that means it is repulsion. All right, keep going. Draw the electric field lines and equal potential lines for each of the following cases. We didn't end up doing this year. All you need to do is the electric field lines. So it says a positive point charge, it's a negative on this. So I'm going to make this positive, correct that to make it match the words. And so then we draw our lines. This is key, is draw those lines first. Always draw your lines, then put arrows. So it's a positive, so it points away. All right, now I have a positive and a negative point charge. How would that look like? Those lines are going to kind of be football shaped. Oh, that one should have been there, and then it would have come down here. Something like that. Now I put my arrows, points away from my positive, towards my negative, and then through the middle, away from positive, towards negative. A lot of you like to say it attracts. There's not any attraction here. This is just showing the field due to these two things. And if I were to place a charge here, then that would feel attraction and repulsion. All right, student measures their resistance. Now we have, looks like an Ohm's law. Student measures their resistance, 100,000 ohms. If he then touches both leads to an electrical outlet, what will the current be running through his body? Well, V equals IR, 120. Times the current times 100,000. Gonna need my calculator for that. 120 divided by 100,000, and I get a current of 0.0012. So not that much current. Still feel it though. If you did this, you would definitely feel it. This is more than the current you felt from the Van de Graaff thing that we did. So you're definitely still going to feel it, but it's not actually going to kill you. The wall outlet's only really going to kill you, and this is like really kill you, if it goes right across your heart and it's got some way to kind of get into your body. So while electricity can be dangerous, unless it hits a certain way, it looks like this particular setup here is not going to end up killing you. So that's what critical. Doesn't mean it's not going to hurt. Doesn't mean it's not going to hurt, like leave injury. It's critical injury, deathly injury. 0.07. It's only 0.002. So is this person in danger? Yes, but not dead. I wish I had changed this. This is kind of a bad idea here. The wall socket will definitely hurt you. 100,000 is not always your resistance there. That's like maybe just your finger or something like that. So, all right, and last page. This is just the homework question again. Potential difference between two plates. So I've got 0 volts up to 21 volts. Then I've got 1, 2, 3, 4, 5, 6, 7 spaces that I need to cover. So this is 0 to 3 volts, 6, 9, 12, 15, and 18 volts. And that means everywhere on each of these lines is these voltages. So rank the points. Well, I've got from increasing. So we want to start down here. So we'll be B. Then we'll go nothing on this line. E and C are the same. Keep going. I got D up at 12. I got nothing. Looks like F is on the 15 line. Even though it's way over here, it's on the 15 line. And then A is on the 18 line. So there's the ranking. Calculate the potential difference as you move between A and the positive plate. So I'm going from 18 to 21. So that'll be 21 minus 18. And that gives me 3 volts. Point B in the negative plate. B is at the negative plate, so there is a 0 volt difference. A and F, if I go from A, which is 18, down to F, even though F is way over here, I could even go this way. I could go up 3, down another 3, or I could just drop to the 15 line, down 3. It's always going to be final minus initial, 15 minus 18, or negative 3 volts. And what is the potential change going from D to E? Well, D down to E, go 6 minus 12, final minus initial, and get negative 6 volts. All right, and last question. Hair dryer on the high setting is a resistance of 11 ohms. Hair dryer is connected to a 120 volt household outlet. What is the current the hair dryer draws on the high setting? V equals IR. 120 again. Don't know current. Solve for 11 ohms. Current comes out to be 120 divided by 11. 10.9 amps. And that's it.